Right? This is sometimes useful for people when they purify proteins. And one procedure of it is they say, if this is my protein of interest, it has a PI of this, they can do a purification step where they say, I'm going to cut out this band or this spot that corresponds to that. So if I have a gradient here, and I know the PI of my expected protein is there, I could say, I'm going to cut this out for further purification. Most purification steps that we do in the biochemistry maybe purifies it 10%. So we usually do about 3 or 4 levels of purification until we're confident in the purity, okay? So that help? Okay. Here's the codon table. You do not need to memorize this, okay? But you should know how to use it. So I can easily give you a DNA strand and say, transcribe this, so you have to figure out the RNA. I can tell you which is template, which is coding, right? By telling you either one, you can make the RNA, and then I can indicate where exons and introns are. So you could, on this question, if I gave you this and said this is the coding strand and told you this is where you start, and then I indicate introns or exons, you could then take and use that information to give me the final mRNA that would be translated, okay? And then you would need to look for the AUG start site, and you can pick the first AUG, because that's methionine, and that would be where you'd start translating, and you'd read them in groups of 3. And then you just pick the answer that corresponds to that. And you use this codon table. So let's go over how you use the codon table, okay? The computer program already has this, of course, programmed in. This is the first position. This is in a 5' to 3' direction, because translation is in a 5' to 3' direction. It moves on the mRNA in a 5' to 3' direction. So the ribosome moves from the left to the right. So if it was an AUG, let's look for this. First position A, second position U, third position G. You see this written out, AUG, and it says methionine, and then has the I after it. That I stands for initiation. I don't like this because there's an I also here for isoleucine. I don't want you to confuse to think this is either methionine or isoleucine. These are definitive. That is, if it's an AAU or an AAA, or a CAU, this is histidine. It's not histidine and sometimes alanine and sometimes glycine. It's always definitive. That doesn't mean there isn't more than one codon for a given amino acid. In fact, like serine has a lot of them, okay? Methionine, only one. All right? Tryptophan, only one. But this is always tryptophan. This is always glycine, etc., okay? There's no, sometimes it's this, sometimes it's not. Here's, sequence. What you're going to do is introduce some mutations. Mutations are changes in the RNA, which contribute to changes in the mRNA, and of course that change, if it's inheritable, had to be in the DNA, okay? Now I was careful there because it turns out, why do I always lose chalk? I'm going to get a chalk holster. So as it turns out, if there's a change in the DNA, that change will be reflected in the RNA. But when we make RNA from DNA, this is not a very faithful process. There's a lot of errors made here. There's no proofreading with RNA. There's proofreading when you make DNA to DNA. So you can get changes in RNA which will affect the protein, but since RNA is short-lived, we don't usually see that as a phenotype. But if there's a mutation in the DNA, that is going to be conveyed to the RNA. Now if it was an intron, which isn't in the final mRNA, would that be important or not? Probably not, but it could be because if this is the intron, which is not in, and we said, we have a mutation here, it may not be that important, but in fact, there's internal information read when this is spliced, and if this was critical for splicing function, and there's a mutation, we may not remove that intron. So there are times a mutation in the intron could potentially yield a phenotype, but typically not. So when the student said no, that's typically the correct answer, okay? But there are times it could. All right, so what you're going to do is go in and just change some nucleotides, and we want you to see how it then changes the protein product. So here, upper one, let's say, was the original. That's a W there, so that was tryptophan there, and now it's S. It's the 208th position. So the notation would be 208th position. Originally was a W, now it's changed to the serine. So mutation-wise, we would write W, which was the original, 208th position, turns amino acid, the polypeptide, to an S. So that would be the notation system you'd use to convey that. At the 208th position, there was a change from the original tryptophan to serine. And you just do a bunch of those. I told you before that you can figure out this. We used to have you calculate molecular weight of various things. I don't know if I do that anymore, but in case you're looking for it, it's down to the right there. Again, complete change about a year ago on this. Again, just various types of mutations. Dr. Patel will spend an entire hour going over mutations, missense, nonsense, etc. There's tons of bioinformatics tools that you can use. You can put in a sequence, it can tell you which restriction enzymes would cut. It can predict folding patterns. So I don't know if you remember that one structure of RNA, it had a complicated structure. Because you can get internal base pairing in that RNA to get 3D structure, hairpin loops, things like that. Primer design. We use primers for the sequencing, right? We use primers for the PCR. You can go through and use programs to say, here's my DNA, how big should the primer be, which of these are better primers? Okay, it can give you information. System analysis is pretty amazing. You can go through and try to look at how are all of the genes in that organism responding to a change. So you can look at all the genes at once. It's pretty remarkable. So you can say, if I give this drug, which of these genes are going up in expression, which are going down? I can then take a disease state. And I can say, here's the disease state, and here's normal. And I can match my drug treatment to how the disease state changes to match the normal, right? So that minimizes side effects, right? If you can get the gene pattern to compensate for the disease with a certain drug, you can start testing. So there are tons of things you can do. This just shows the results of a blast in terms of various hits. These are scores. These are probability values. That means what's the chance you get that match just randomly? And that's a very low number, okay? So the lower E value, the better the match, okay? All right? And that's the part with the oligopeptides, trying to introduce, disease, things like that. Doctors, people in clinical professions, they're doing this stuff all the time, trying to figure out various things, getting into the database that way, okay? If you remember, we had you do the sequencing stuff, right? So we started out by saying, what are these bioluminescent bacteria? And we had you sequence 2 genes, the 16S ribosomal RNA and the RNA polymerase B gene. So what you're going to get back is data that looks like this. So here's the data you're going to get. It's going to be a file like this. These are the actual traces. That's what we saw. Well, that's what the laser and the computer detected. And we see various things like that. And there are places where it's not sure what to call it. So it puts an N in there. So you're going to go through, do some steps, basically try to clean up various things and say, okay, yeah, this couldn't call it before, but I can eyeball this and see that there's a red peak there. But if you notice, there's a black peak coming down. So this red peak is probably the real data point. But the computer couldn't distinguish between that red and black. You can look and say, oh yeah, that's probably the red is the T. So you'll artificially go in and change that from an N to a T. So you'll clean up the sequence. Okay, so remember what we did was we did 2 sequencing reactions. So for the 16S, we have in the background that large chromosomal DNA. And those primers are nailed to 2 specific spots. So what we did was we did our PCR, so we had double strand product, but when we denatured it, and we anneal a forward primer there and a reverse primer there, and we start sequencing this, we're getting data along that run. We're getting data along this. And at the end, it's not real good because it's hard to get separation, et cetera, et cetera. But at the end, it's not real good. But what we're trying to do is say, let's clean up this sequence, call that the forward sequence. This is the reverse sequence. We clean that up. And then what we can do is just say, okay, now that we've cleaned this up, let the computer take and just get the reverse complement. So the computer will say, okay, let's flip this around and do this. And match it like that. And what we're looking for is overlaps here, okay? All right? So typically what happens is we'll see overlap here so we can get good data the entire length. And that's called consensus. And it's consensus that will blast against the database. And what we're trying to do is there's information there for many, 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 many species. Some of them aren't even identified. All they know is the 16S sequence. So you're going to take your 16S and blast against that database and come up with some results. And if you just clean up the data, it's pretty straightforward to do that sort of thing. You clean it up. Remember the overlap? Here just goes through here. And then what you do is go through and basically do alignments. And this was for a class. So this was just, we took various groups and aligned their data. But what you're going to do is just blast it with both the 16S and the RPOB. Yes, question? I'm sorry? Oh, how to go over the N? This is post empty space is also here. I'll just go over it quickly here. Okay, so right here. So if I look here, there's an N. So if you look at the tracing, it goes black peak, it called it a G, a black peak, it called it a G, and now at this position, the black peak is decreasing in intensity and the red is increasing. But if you notice, the black and red are about the same intensity. So the computer doesn't know, should I call it a G or a T? It doesn't know, right? So it says, okay, so I don't know if it's the T or the G, but I eyeball this and say it's a red peak that's really the true data point, so you just go in there and make it a T. Make sense? And so you'll just do that. Sometimes you can't change it, and you have to leave it as N. So sometimes you can't be any better than the computer, but many times you can. Okay? And when you get these data, we're going to have you do a tree building exercise. And I know this is all kind of, what am I really doing? Once you're in the lab actually doing the data, it'll make sense. So here's some various data here, and I just want to go over what this is showing. How many have had Bi1b? Cladograms, we'll do a lot of this the second half of the course, showing relationships. But what this says is, in this case, it was 2 DNA sequences, because we didn't say what species it was. When you do your blast, you'll get back information about the names of species, okay? So instead of calling this a sequence, it will say, what this species is and what this species is. So let's look at this. That means this is a common point for these two. These two sequences, or species, were descendants of this. There's a common ancestor. Here's a common ancestor of this group and this group. So these are nodes, okay? So in this situation, these two are more closely related than, this node and this node, and then we have nodes here. So it's trying to go through and determine relationships. This says you can make relationships strictly based on DNA sequences, or if you match those two species, you can change it and just substitute with species names. Is that clear? People are doing this constantly. They sequence DNA, figure out relationships. Okay, so I'd like to now go over the genetic stuff, okay? Because this is the stuff that's, I think, the hardest. Okay, so right now, if you could write a sentence with those 4 words in it, try to convey that, and likewise for this, okay? All those words in a given sentence. 2 examples, A and B. And then I need a volunteer. So whoever wants to volunteer, come up. Who wants to volunteer? Oh, he does. Okay, great. Come on up. She just nominated you as volunteer. It's really difficult. Put your favorite 3 letters on the board. Erase that board and put your favorite 3 letters. English. There's only one. I'm always looking for it, too. Okay. So while the student's putting up his favorite 3 letters on the board, it's not a struggle, right? Just 3 letters, English letters. Do you need help? A, B, K. Excellent. Thank you. That's it. All right. So first off, I now going to take that information to do a biological proof. It's 3 letters, but how many of you were able to get a sentence with things like sister chromatids, centromere, microtubule, and separation? So you could say the chromosome, after replication, consists of sister chromatids. The microtubule is attached at the centromere, and they separate the chromatids, right? Something like that. Or you could have said homologous chromosomes pair up during prophase 1, and crossing over occurs amongst that, right? So do you remember last time I said, take my word for this, that the double recombinants are the lowest number, and the largest number is parentals? And what did I tell you to find the one that's in the middle? What did you look for? The one that was different. Okay? And why are the double recombinants the lowest? I didn't go over it last time, but if I take this example here, the letters A, B, K, and I'm just going to write it like this, where the 3 wild types are on the same chromosome, and the 3 non-wild types are on the same chromosome. So this is the coupling relationship. The parental types of gametes would be A, B, K, and the other parental would be A plus, B plus, K plus. Is there anyone who does not see that? Okay, great. Now the recombinant between A and B only would be, again, this is where this notation system is so powerful, crossing over between here. So it would be A, B plus, K plus, and A plus, B, K. Anyone not see that? Okay, excellent. Now the recombinant between B and C would be A, B, K plus, and A plus, B plus, K. Anyone not see that? Excellent. Now the double recombinants, where there's a recombination between A and B, and between B and C, would be A, B plus K, and A plus, B, K plus. Anyone not see that? Raise your hand if you don't see it. So I cross over once, so it goes A, B plus K plus. Since I cross over a second time, it goes A, B plus K, and A plus, B, K plus. Since recombination is a number less than 1, so if this was 0.2, and this was 0.1 for the 2 categories, this number always has to be the lowest number, because it's a number less than 1 times a number less than 1, so this would be 0.02. So the double recombinants always have to be the lowest number mathematically, always. No exception. Now, let's just take one of these and compare it to the parental, which is the largest number. So in this case, what's the percentage of parentals? If this is 0.02 for these, 0.2 for this, that's 20%, plus 10 is 30, plus 2 is 32. That means this has to be 68%, 0.34, 0.34. Because they have to equal 100%, right? A, B plus K. If I look at this one, the A is different, and the K is different, so I chose the wrong parent to look at. So all I do is say, whoops, I looked at the wrong parent, because there can only be one difference, or I could just pick a different double recombinant. Now if I look here, the one that's different is the B, correct? That's the one that's in the middle. That's universal. Whether I switch these letters to any letters in the alphabet, it doesn't change the logic that's used. So look at the double recombinants, find the one that's different than the parent, that's the one that's in the middle. You just map them, okay? So let's quick do this problem here. So which of these are the double recombinants? The 10, right? That's the lowest number. Which are the parentals? Which boxes? The ones with the 280. So let's look at this. This versus that. The T is different. Only the T is different, right? So what's in the middle? T. So you rewrite these to put the T in the middle. So I'd write this STP, S plus, T plus P plus, S T plus P plus. And the reason why I would rewrite them is because later on, if I ask you for the map distance, you need to have them in the correct order. So let's just quick do that. I think I did that here. I rewrote them in the correct order now. All I did was I moved the T in the middle. It does not matter if I put this as PTS or STP. It means the exact same thing. Any questions about how you figure out what the double recombinants are? Yes. What does C mean? Where do you see C? Oh, I'm sorry. This should have been a K. He chose the letter K. I'm sorry. Okay. So he chose the letters A and B. So recombinant between A and B. And then he chose the letter K, and I was sloppy and thought he chose C, because that's how we would have taught it, because it's easier. And so I was sloppy here, and I should have written K there. Does that help? Did I do a KC mistake somewhere else? What's that? Does it confuse you enough I need to redo it all? Yes? You're okay, right? Did I make those numbers up? Indeed, I did, because the data comes from either making it up or I get it from real data. Some of you may remember I did that several times last time. I either make up the data to do the problem, or I would look at an actual cross and get the data from the actual cross. Yes? So the question is, did I calculate the 0.02 using previous data? I just to teach, I made it up. And what I made up was the following. I made this up as 20 map units. I randomly chose 20. I made this up as randomly 10%. This was not random. This is this times that. And then this number came from the other numbers. But if I did an actual cross, like you did in lab, I would see actual data, so I wouldn't have to make it up. I'd do the mating, and I'd say, hey, I saw one individual like this, and one like that, and 6 like this, and 4 like that, and 11 like this, and 9 like that, and 33 like this, and 35 like that, or something. That would be the actual data I would get. So I either make up the data to do the problem, or I get it from actual data. Okay? And this is always a question students ask repeatedly. So I either make it up, or I get it from data. Is that clear? Yeah. So the question is, how does putting T in the middle allow us to get the map distance? So let's do that, okay? So is there anyone who needs me to go over how I got T in the middle? 3, 4 hands. Okay, so let's just do this again. Any questions about how these are parentals? Yes or no? No. Any questions about how these are recombinants between A and B? No. Any questions about how these are recombinants between B and K? No. Any questions about how these are double recombinants? No. Yes? Okay, there was several yeses, so I'm going to go over that. With our notation system, notice how if this came down once and was a crossover between there, it would be A, B plus K plus. Right? Which we wrote there. But that's one recombination between A and B, and we want a second. So I have to do another crossover, because it's 2 double between here and here. So if I color code this, we'll do that. There's the A, the B, the K, not C. Here's the A plus, B plus, K plus. I'm going to ignore these chromatids out here, but I'll write them so you don't think they just suddenly disappeared. So when I break and rejoin, I get A, B plus K, and A plus B, K plus. Is that now clear? Yes or no? Yes? And just because we artificially said, hey, let's put 3 letters in this order, we can always apply this, just change the letters. So what we saw was, if we look at this versus the parental, the one that is different is the one that's in the middle, because the recombination were between these two. Okay? So it's always applicable, just the letters change. Okay? So all we've done here is change the letters to T, S, and P, and whatever, okay? Yes, question? So the question is, why is it guaranteed? Because we've just done a proof. If you can draw something that comes up with something else, show me, okay? It's always true. We did something randomly, and we've shown that it works for that case. It will always work for every case. It's a proof. It's like a math proof, okay? It's called biological proof, okay? Can't answer it better than that, sorry. Okay, let's do some application. So now we wrote these in the correct order. So I'd like you to come up with the map distance between S and T. What's the actual map distance between S and T? You see the struggle I face trying to teach some of this stuff sometimes, right? So now do it between S and T. I want everyone to be on the same page, S and T. Okay, who's got the answer? No one has the answer? Okay, I'll give you more time.